All right, Chapter 2, Section 8, the derivative as a function. So far we've looked at derivatives as the slope of a line tangent at a given point. So up to now, a particular value of a has been given for our questions. But a itself can be a variable. We don't have to lock ourselves down to a specific input value of a. We can leave that as a variable. And of course, the most popular variable that algebra likes is x. So what we could do is take our derivative definition that we've been working with, right? And then instead of an a, we could use any letter we want. There's nothing special about the letter a. It represents an input value, right? So up to now, all our questions have been framed in a way where a is a number, right? Find the slope of the line tangent when x equals to 7 or when a equals to 4, right? Some specific value that we input for the value a. But we don't have to leave it alone. We could use b, we can use w, we can use any letter we like. So, of course, algebra loves x. So we can just change it. So all we need to note here is that the only thing that changes is that instead of using the letter a, we use the letter x. Okay? Everything else is exactly the same. X is a variable in the domain of our function, and this is the derivative of that function, meaning that once a value is chosen for x, we can apply this limit, and if the limit exists, then that will be the slope of the line tangent to the point x comma f of x. Okay, that's all this is. So when we do that, when we acknowledge that this itself is a variable, to be determined, then f prime of x is a function itself. It's a function where you input a value x and the output is the slope of the line tangent at that point. As a quick example, let's say, for example, f of x is defined to be 3x squared plus 1. If we take the derivative of this, so let's find f prime of x, we know that this is, by definition, equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. And we know that if we plug in that function, we get the limit as h goes to 0 of 3 blank squared plus 1 minus 3 blank squared plus 1 all over h. And we have to be careful that this minus applies to this entire function, so put in some extra parentheses. So it's the first function minus the back function. So the first one will be an x plus h, and this back one is just x. Okay, so foiling this out, we get f prime of x is equal to the limit as h goes to 0. And I'm going to rewrite this 1 over h over here. Makes it a little easier. And it'll be 3 times, and then if I FOIL this out, I'll get an x squared plus 2xh plus h squared plus 1, plus 1 minus, and then this is just 3x squared plus 1. So f prime of x is equal to the limit as h goes to 0 of 1 over h, and then distributing that 3, we get 3x squared plus 6xh plus 3h squared plus 1 minus 3x squared minus 1. Good. Luckily, a bunch of stuff reduces now. We see that the minus 3x squared will cancel with this 3x squared. And the minus 1 cancels with the plus 1. And so these are the only two terms left standing. So f prime of x equals to the limit as h goes to 0 of 1 over h 6xh plus 3h squared. Okay, so we can factor out an h. So we get f prime of x equals to the limit as h goes to 0 of 1 over h, and then if I factor out an h, I'll get an h, and then 6x plus 3h. The h's cancel, finally, and we've achieved our goal, right? Because we know from our work with limits that if we have a polynomial and we're trying to find the limit, all we have to do is evaluate that polynomial at the value of the limit. If we have a rational function, then it's the same thing. We can just evaluate the rational function by plugging in that value. However, there's only a caveat there. We can't let ourselves divide by 0. So at this stage up here, if I had replaced all those h's with a 0, I would be dividing by 0. Same here, I would be dividing by 0. That's why we can't do that yet. Our goal is to come up with some way of manipulating our statement into an equivalent algebraic statement such that the h's can be canceled or otherwise transformed in a way that if I replace h with a 0, I won't be dividing by 0. And that's what we finally achieved here. So now that that has been canceled, we get that the derivative of x is equal to the limit as h goes to 0 of 6x plus 3h, which is a polynomial. Okay, and as I just said, we know that when we have a polynomial and we're trying to find the limit of a polynomial, all we have to do is evaluate that polynomial at that value of our limit, and that'll be equal to our limit. So that means that the derivative with respect to x is going to be equal to 6x plus 3 times blank, and we're going to replace that h with a 0 from there, right? That's what we're trying to do. And so we just end up with 6x as our answer. So from here we get that f prime of x equals to 6x. Okay, so putting it over here, we have the original function here, and now we have this derivative function f prime of x, which is equal to 6x. Okay, so note that to interpret this, note that, for example, if x equals to 4, what does that mean? Okay, so we put in a 4 into our function. We get 3 blank squared plus 1. So if we input x equals to 4, we'll get 16 times 3, that's 48, plus 1 is 49. So we get 49, f of 4. Okay. On the other hand, if we go f prime of 4, on the other hand, if we look at the derivative function and we evaluate it at 4, what does that mean? We get a 4 there, we get a 4 there, we get a 24. So f prime of 4 equals to 24. Okay, let's interpret what these mean. This is establishing an input-output relationship between the x-coordinate independent variable and the y-coordinate, right? So when you input a 4, right, the input is 4, the output is 49, output, which is, this is going to be a 4 comma 49. This is a point, an ordered pair on a Cartesian coordinate system. On the other hand, this, when you input a 4, this 24 is the slope of the line tangent to the function at this point. 4 comma 49. Okay, but this establishes an ordered pair in its own right. It's the ordered pair 4 comma 24. So if I was going to graph all the slopes of all the lines tangent to the function f, and I graphed those, then this would be an ordered pair in that graph. Okay, so we're going to take a closer look at the graphs of the derivative function and how it relates to the graph of the underlying function. And we'll come back to these functions in a second, but let's begin by looking at something a little bit different, and then we'll come back to this in a little bit. Okay, so let's say that we're given this function here. Don't worry about the equation, but we want to think about what would the graph of the derivative function look like, the graph of the derivative function. The graph of the derivative function will be a graph where you input the x-coordinate, and the output of that function will be the slope of the line tangent at that point to the point given here, right? So if we let x equal to b, for example, right? So there's some b value here. Then this will translate to some point there, which is the point b comma f of b. And now if we plug in b into the derivative function, the output will be the slope of the line tangent at that point, which we can visualize, maybe something like that. Now, since I don't have the actual equation, I don't know what that number is, so we won't be able to come up with the exact numbers, and we won't be able to come up with the exact graph. But even if we don't have the exact numbers, even if we don't have the exact equation, we can still tell a little something about our graph. So first of all, the easiest thing we can think about is, when will it be 0? Remember that the slope of a horizontal line is 0. So if I think about those tangent lines, hopefully it's clear that somewhere around here, somewhere around there, we're going to have a slope of 0. Slope equals to 0 right around there. And also the slope is going to be 0 right around there somewhere. And likewise, it's going to be 0 somewhere around here. So if I was graphing a function, if I was graphing the derivative function, I could tell that somewhere around here, ballparking it, somewhere around there, we would have a value of 0 on that graph. It would be a place where that graph crosses the x-axis. Same for a point somewhere around there. Let me erase this b, we don't need it right now. Get rid of that. Okay, so these are the easy places. Wherever the tangent line is horizontal, the slope is going to be 0. Okay, what else can we tell? Well, remember, we're looking at the slope of the tangent lines. So in this zone right here, when I draw my tangent lines, they're going to have something in common. Okay, as I put more and more tangent lines around here, the one thing we can identify is that they're all going to have a positive slope, right? The slope is always positive. It's going to be some very small positive down here, and then it gets bigger and bigger and bigger and bigger, and then it starts to get smaller and smaller again. In this entire zone, from there to there, in that entire zone, all the tangent lines are going to have positive slopes. That's what we're trying to identify here. So in this zone, slopes are positive. Okay. Likewise, if I think about this giant section from here to here, let me highlight it. If I go from here all the way out to here, and I think about all the lines that are tangent there, I can draw a line, a tangent line like this. Okay, so if I think about all the different tangent lines I can draw, they always have a negative slope. So all throughout the green highlighted portion, all the slopes are going to be negative. Therefore, when I graph the derivative function in this green zone, which translates to a segment along the domain, right? So this from there to say there, in this zone from there to there, it must mean that in that region, the derivative is below the x-axis. The graph of the derivative will be below the x-axis. In this zone here, which comes down to the yellow, right, in this little segment over here, from there to there, when I graph the derivative function, it should all be above the x-axis, right? So that's because all the slopes are positive. So this should be above x-axis. And then over here, this zone, in this little region here, it should be below. Good. And now what about in this zone? Okay, so if we think about all the tangent lines in this little zone over here, we can draw tangent lines that connect this way. I can draw tangent lines that extend out this way. And again, we can see that they are all going to have a positive slope going this way, right? All the tangent lines are going to have a positive slope. So if I think about this portion of my graph, and I translate it back to a portion on the x-axis, and as I translate it back to there, in this portion of the x-axis, when I graph my derivative function, the derivative function should be above the x-axis. Above. They should have positives, right? The slopes are all positives here. Now, in fact, if we get close to here, so it's 0 there, but if we go just a little bit past that, then we're going to have a small positive slope, say somewhere around here. Small positive slope in this area, right? If you think about the tangent lines there. And then way up here, we're going to have a very large positive slope, right? As we see this. Okay, same thing over here. If we get really close to the horizontal is 0, but if we go just a little bit past that, right at the beginning here, we're going to have, right around there, we're going to have very small negative slopes. And then likewise over here, we have 0, the slope is 0 here, and then a little bit below that, we're going to have a very small negative slope there as well. Small negative slope. Okay, so when is the biggest negative slope? When is the steepest in the negative direction going to happen? It's going to be somewhere around the middle, right? This is going to be the largest, the biggest. Big negative slope, somewhere near that middle part of the graph. Good. So as I graph the derivative function, I know this is going to be below the x-axis. I'm going to start off by having a small negative, bigger negative, until I reach the biggest negative possible, and then back to a smaller negative, and then to a 0. Okay, I'll use technology to improve on this, since I think it just kind of made a bit of a mess here. But we have a nice little picture your book provides for this, so let's take a look at it. Okay, so as I tried to point out, we have all the places where the tangent line is 0. That's going to be these 3 spots. If I try and graph the derivative, then that means that the slope of the line tangent will be 0. That means that it crosses the 0 axis at these 3 points. Okay? And then as I was trying to point out before, if I think about all those tangent lines, all the tangent lines between point B and point C, all the tangent lines are going to have a negative slope. That means that between point B and point C, the derivative is going to be negative. It's going to be below the x-axis. Okay. Now note that at the very beginning up here, right after B, the slope is going to be a small negative, right? If I think of a tangent line right around here, like right around there, it's not going to be as steep as one that's like right over there, right? So the tangent line there is going to be much steeper than this one. So it starts off at 0, then a small negative, bigger negative, bigger negative, bigger negative, and that's what this is describing. Small negative, bigger negative, bigger negative, bigger negative, bigger negative. And we reach the biggest negative slope somewhere near the middle here. That's when it's the steepest in the negative direction. And then we begin to get smaller negatives and smaller negatives and smaller negatives. And then eventually we get back to 0. And that's what this is describing here. Smaller negative, smaller negative, smaller negative. Okay. Beyond C, we see that all the slopes are positive. That's a positive slope. That's a positive slope. That's a positive slope. So the slopes are all positive. They start off at 0. They get a little bit bigger, and then they just keep getting bigger and bigger and bigger and bigger, and it just kind of shoots off that way. So this shoots off that way. Good. In between point A and B, all of these slopes are also going to be very tangent lines that connect this way, and they're all going to be positive slopes. So a small positive, bigger positive, bigger positive. We reach the biggest positive slope somewhere near the middle here, and then it comes down again and we go back to zero. And that's what this is describing. We start off at a zero slope at point A, and then as we move a little bit to the right, we get slightly larger positives, bigger positives, bigger positives, bigger positives. We experience the largest positive slope somewhere near the middle of this graph. And then we begin to slow it back down again, and the angle gets a little bit smaller, and we get closer and closer and closer to zero again. So that's what this describes. Okay, and then finally over here we have all negatives. These are all negative slopes. They start off at zero, and then a bigger negative until we go this way until we get a infinitely large negative, and that's why it shoots off toward negative infinity in this direction. Okay, so this is a rough sketch, right? If we were given that this guy here, this function is f of x, then this would be a graph of its derivative. Okay, so now there's a few things that we can definitely tell. We can definitely tell where these are zeros. That's when the line is horizontal. What we cannot really tell is just how big these loops are. So, we don't really have exact numbers for this. If someone wanted to argue that this was a little bit bigger and came down, then, it's kind of hard to say by just the graph. So don't worry about the exact precision. How do we know that this bump goes up to there and this bump comes all the way down to here and goes that way? That's something that we're going to work on in the next couple of chapters, getting more information about this derivative. How do we find that maximum, for example, or this minimum? How do we know that it has this curvature to it here? See how it kind of has this curvature? We'll think about that in the next coming sections. But for now, we just want to get a rough idea. Let me use Desmos. Actually, is it Desmos? Yeah, maybe Desmos, to get a better sense of this. Okay, let's say that we were working with this blue function here, f of x. The equation's up here, but don't worry about what the equation is. I just picked some weird-looking thing, just something that gave me lots of wiggles here to work with. And I already set up Desmos to automatically give me those tangent lines. So as I move this, as we travel along my f of x function, we can see the tangent functions, right? So if I wanted to, I don't know if it'll make it, well, that's fine. So let's label it. So here we have an input-output pair for our function, but then we also have the slope of the line tangent. So some of those are really easy to spot, like let's say, for example, right around there. So, for example, there, the tangent line is horizontal, so I know that the derivative will be 0 at this point. So if I was going to graph a graph of the derivative function, I would have an ordered pair at 2, 0. Right? So let's do that here. I've arranged this table that will automatically give us the values of the derivative. So if we put in a 2 here, see, it automatically gives me a 0. 2, 0, and it puts a little dot there to show that that's what the slope is at that point. Okay, all right, let's find another one. Another easy one is over here. Another easy one is when x equals to -1. At -1, we have an output of 10, but we see that the tangent line is going to be horizontal there, and I can confirm that again with my table over here. So at -1, the derivative is going to be 0. The horizontal line is 0, and that gives me another ordered pair, which is going to be this little guy right here. So the little green dots are already identifying 2 points on my derivative function. Good. There's a couple of other places where it's going to be 0, but this is not going to cooperate very well. So somewhere around there, there's going to be a 0. And also down here, somewhere down here, there's going to be a 0, somewhere between these values here, but it doesn't want to play very nicely with me. So somewhere around here, there's something that's going to be horizontal, right? Okay, so let's consider this part of the graph here. You see how all of these slopes are negative? We start off with a very big negative slope over here. And then as we get closer and closer and closer to the right, we see that the slopes get smaller and smaller and smaller and smaller. You might have noticed this little value right in here. This is automatically telling me the slope. That's Desmos, I set it up that way. So at this point, this is letting me know that when the input is 2.74, the output is negative 20.774. That's this ordered pair on the blue graph. And the slope of the red line is negative 52. So if we keep track of that, we see that way up here, the slopes are very big negative numbers. They start off as very big numbers, and as I move a little bit closer and closer to the right, that negative slope keeps getting smaller and smaller and smaller and smaller and smaller until it slowly reaches to 0, and then it becomes a small positive. So somewhere between there and there, it should cross over into a positive. And then from this point forward, the slopes are positive. So we have a very small positive, and then a bigger positive, and then a bigger positive, and a bigger positive. We reach the biggest positive we will reach in this portion of the graph. And then it's still positive, but gets a little bit smaller, a little bit smaller, smaller, until it goes back to 0. And then it's positive again. Small positive, bigger positive, bigger positive, bigger positive, bigger positive. We reach the biggest positive we're going to get in this portion of the graph right around in the middle there. And then we get a smaller positive, smaller positive, smaller positive, smaller positive, back to 0. Then a small negative, bigger negative, bigger negative, bigger negative, bigger negative, bigger negative. The biggest negative slope we're going to get is somewhere around there. And then we go back to a smaller negative slope, smaller negative slope. We reach 0 somewhere around there, and then we go toward a small positive, bigger positive, bigger positive, bigger positive, bigger positive. Okay? So if we're going to graph all those things, if we wanted to trace those values of our slope, let's just think of a few points. So let's say around here, we know we were going to get really big negative values. Then it started to get really close to here around negative 2.5 leads to positive 15. Negative 2.6 leads to negative 16. Okay, so I graphed a few points on my derivatives. I found a few of those derivative values, and we can see that they start to give you those points right around there. Okay, so we can see that somewhere around here we have negative, small negative slopes, and then we hit 0, we punch through 0, we start to get small positive slopes. We see that somewhere near the middle of this, we experience the biggest positive slopes we're going to experience in this portion of the graph, somewhere around there. So it looks like somewhere around negative 2. Let's figure out what those slopes are going to be around negative 2. So negative 1.9, negative 2, negative 2.1. We start to see that they form values up here somewhere. And then as we come this way, we see that the slopes are getting smaller and smaller and smaller until they go to 0. And then they start to get bigger and bigger and bigger again. Okay, so if we get some points from around here, this is going to be somewhere around negative 1.5, negative 1.4. Okay, so we see that we start to see some points there. The slope is a very small positive slope all through here. So the slopes are getting smaller and smaller and smaller. That's why we have these green dots that are getting closer and closer to 0. Eventually, when we hit negative 1, we're going to get 0, and then they're going to become small positive numbers again. So they come down, they touch at negative 1, and then they continue to climb. Again, somewhere around here, we experience the biggest positive slope we're going to experience in this portion of the graph. Somewhere around there. Looks like somewhere in the neighborhood of 0.22. Be a good place to graph a few points. So let's graph the point 0.22, 0.23, 0.24, 0.25. Okay, so we start to see that there's a little bit of a curve here. Again, we started off at 0 here. The slope of the red line becomes a small positive number, bigger positive number, bigger positive. We experience somewhere around here the biggest value, the biggest positive slope, and then they begin to get a little bit smaller and a little bit smaller again until they go back to 0-ish. So right around 0.9-ish, somewhere around there, they're going to go all the way down to 0. So say 0.7. Okay, and you see they cross down to 0, and then they go down into the negatives. And that's what's happening here. The slope is a very small positive slope, but then it's getting smaller and smaller, positive still, but smaller and smaller until we're going to hit 0, and then it turns into a small negative. Smaller negative, bigger negative, bigger negative, bigger negative. So we see that those values are going to start to come down into the negatives, and we're going to experience our biggest negative slope somewhere in the middle here. Looks like I see like a negative 46-ish somewhere. So right around there, at around 1.5, we will experience the biggest negative slopes. So let's graph a few points around there. So 1.5. 1.5 leads to 40 something, so that's way over there. There it is. 1.4, 1.6, 1.7. So what we should be getting out of here is, again, we started with very small positive slopes there, smaller positive. We got to 0, punched through to the other side, became a small negative slope, bigger negative slope, bigger negative, bigger slope. We reached the biggest negative slope somewhere around here, and then we got to get smaller negative, smaller negative, smaller negative slope, smaller negative slope until we go back to 0, and then it's going to punch through to the other side and become a small positive slope somewhere past 2. So let's graph some points around there. That'll be like a 2.1. Ooh, that jumped really quickly. About 2.01, 2.02, 2.03. Okay, so we have a bunch of individual ordered pairs, right? Keep in mind that what this means is that 35 is the slope of the line tangent at the point when the input is negative 1.9, right? Okay, so all these dots, if I kept going and found all of them, eventually they will all form this very smooth curvature. And so the green one is the graph of the derivative of the blue one. All right, so let's get rid of these dots. A lot of stuff happening here. And let's once again confirm the derivative starting over here. So you see how these tangent lines are going to have a very big negative slope. That's why the green one starts off from way down here, very big negatives. And then as the tangent line gets closer and closer and closer to, looks like around negative 2.5-ish, the slope here is going to be a small negative, smaller than before, and then it slowly, very slowly changes until something that's close to 0. That's why the green line gets smaller negatives until it equals to 0 at some point. So from Desmos, I can tell that it's going to be there. At negative 2.573, the slope is going to be 0. Okay, so if I can put that into here, I would get that. Okay, so we'll have a 0 there, and then it becomes a small positive after that. Small positive, bigger positive, bigger positive, bigger positive. That's why the green line gets bigger and bigger and bigger and bigger. And it experiences the biggest positive slope somewhere around here, which is going to be this, corresponding to the top of that guy. So I can see that the biggest slope is going to be 42.626, and it's going to be experienced with the x coordinate is negative 2.142. Okay, Then the slope gets smaller positive, smaller positive, smaller positive, back to 0. So the slope is getting smaller and smaller, close back to 0. And then it continues to get positive, right? So we started off as smaller positive to 0, and then a small positive, bigger positive, still positive, until we reach the maximum point somewhere around here, which is going to correspond to the top of that peak there. And then it'll get to be smaller positive until we get to 0, right? That's why this comes back down to there, crosses 0. Then it's a small negative, bigger negative, the biggest negative corresponding to this value down here. And then a smaller negative until we get to 0. Then the small positive, bigger positive, all the way out through there. Okay, so the blue function is the blue is our f of x function. Then the green would be our derivative function. We'll try a different technology. Okay, so now let's try this one. Let's say that our original function is just the function x squared, and we're thinking about the derivatives. At this point, the tangent line is horizontal, so it's going to have a slope of 0. So it'll be 1 dot 0 comma 0 on the graph of the derivative. And as I move this in this direction, as I move this way, the slope becomes positive. At first, it's going to be a very, very small positive, and then it gets bigger positive. And as I continue, I see that this line here represents the slopes that I'm achieving. They're all positive, and they're growing that way. Okay? And then as I go back this way, after I go back to 0, as I go back through 0 and into the other direction, the slopes now become a small negative, bigger negative, bigger negative, bigger negative, bigger negative, bigger negative. And so that black line that begins to be traced out is the graph of this function. Okay, so I can show that the derivative is that. If I kept going, eventually this blue line here would be the graph of the derivative of this function. Okay, let's try something else. Okay, so let's say we have this function here. The tangent line will be horizontal at this point. So we'd have the ordered pair 0, 0 in the graph of the derivative function. And we see that as we move forward a little bit, we see that the slope becomes negative. A small negative, bigger negative, bigger negative, bigger negative. We achieve the biggest negative somewhere around there. And then the slope is going to become smaller and smaller negative, all the way up until we get 0, right? So somewhere around here, we will have 0 again. And then as we move forward, we see a small positive slope, bigger positive, and it just goes out of control in the positive direction. Really big positive slopes over there, really big positive slopes. So the graph, the derivative, will just shoot up that way because they're very big positive slopes over there. Let's go back to where we were. So we started off here with the slope of 0. Now, if we move in the other direction, we start off with a very small positive slope, bigger positive in this direction until we reach somewhere around here. The biggest positive slope we're going to achieve is somewhere around here. And then the slopes are still positive, but they're smaller and smaller until we get to 0, somewhere around here. Until we get to 0, somewhere around there, and then the slopes become small negative, bigger negative. Okay, so if we keep doing that, we keep tracing this all the way throughout, we get a better and better image of what the graph of the derivative function is going to look like. Okay, so we start off with very, very large negative slopes of the tangent line are very large negative values around here. They become smaller negative. We hit 0 somewhere around there. Turns into a small positive, bigger positive. The biggest positive, smaller positive, 0. Small negative, biggest negative, small negative, back to 0. Small positive, bigger positive, really biggest positive. Okay, so if we keep doing that, eventually we would get to this, and that would be the graph of the derivative function. Okay, we'll have more opportunity to practice with those later. So let's go back to the one we did in the very beginning. So we had 3x to the second power plus 1. Let's graph that. So here's the graph we were working with, and we found that the derivative was equal to 6x. So the slope is 0 there, and then as I go this way, as I move to the right, I get a small positive, bigger positive, really big positive, really big positives. Go back to 0, and then if I go in this direction, I get a small negative, bigger negative, bigger negative, bigger and bigger negative. So eventually, they look like this. So that solid blue line is eventually the graph of my derivative function. And we can see here that it's equal to 6x. That's what we got. Okay, so let's see. Given that f of x equals to x minus 2x cubed, find f prime of x. Find the derivative. So let's begin by setting up our limit. So we know that f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay. Now we're going to evaluate each of these functions at these points. So let's copy this. Limit as h goes to 0 of blank minus twice blank cubed minus, and then we're going to have a blank minus 2 blank cubed. Now we have to be careful because this subtraction applies to all of that. So let's put parentheses around the whole thing. And then, of course, the whole thing gets divided by an h. Okay, so here we're going to put an x plus h and an x plus h there. And here we're going to put an x and an x there. So that's from this being evaluated into there. So that's how we get this and this. Blank minus, right, the input minus 2 times the input cubed, where this is the input for the first function. And for the second function, well, this is the input, which seems a little silly because you're just kind of copying the function, but it's because we use x way too much. Okay, now remember, our goal now is going to be to figure out a way to simplify, reduce, cancel, whatever we need to do, get to a point where we can plug in h as 0 and not be dividing by 0. We know from our work with limits that if we have a rational function and we're trying to find the limit, then it's equivalent to just evaluating that rational function at that value of our limit as long as we don't divide by 0. Okay, so we're going to have to do a little bit of foiling here. So note that if we have x plus h squared, that's going to be x squared plus twice xh plus h squared. And if we have x plus h cubed, well, that's just going to be equal to x plus h squared times another copy of x plus h. And this one we already had there, so that would be x squared plus 2xh plus h squared times another copy of x plus h. So I have to FOIL this whole thing out. So x times each of these terms plus h times each of these terms. So I'll have x cubed plus 2x squared h plus xh squared, multiplying each of these terms by an x. And now coming back and multiplying each of those terms by an h, I'll get plus x squared h plus 2xh squared plus h cubed, which then simplifies to x cubed plus 2x squared h, I'm sorry, not 2, 3, 3 copies of, kind of adding all of these guys up, 3 copies of x squared h plus another 3 copies of xh squared plus an h cubed. Okay, so you either do it the long way, like I did here, or if you have it memorized, then that's okay. There's a nice little pattern that happens for those. Okay, so let's come back over here. This is the derivative equals to the limit as h goes to 0. And then another thing I'm going to do is I'm going to rewrite this as multiplying by 1 over h. Makes it a little easier. So I'll have an x plus h minus twice, and then I just figured out what that whole product is going to be. That's going to be this x cubed plus 3x squared h plus 3xh squared plus h cubed minus, and now be careful, this subtraction applies to both terms, so it'll be minus x and then plus 2x cubed. Okay, so let's distribute this minus. We get f prime of x is equal to the limit as h goes to 0 of 1 over h, and we get an x plus an h minus a 2x cubed minus a 6x squared h minus another 6 xh squared minus a 2h cubed minus x plus 2x cubed. Okay, so luckily a bunch of stuff will cancel now. We have a plus x and a minus x. Those two will cancel. And we have a minus 2x cubed and a plus 2x cubed. Those will cancel. And so this guy survives, this term survives, this term survives, and that term survives. So let's copy those. Okay. So now all the terms that we have remaining here all have a factor of h. So we can factor one h out, and then that'll reduce with this h. Cancels with that guy. And what we have is something that's just going to be a polynomial. F prime of x is equal to the limit as h goes to 0 of 1 minus 6x squared minus 6xh minus 2h squared, and this is just a polynomial. We know from our work with limits that when we're trying to find the limit of a polynomial, all we have to do is evaluate that polynomial at that value. So this simplifies as f prime of x is equal to the limit as h goes to 0 of, oops, we don't need the limit anymore. So this is going to be equal to 1 minus 6x squared minus 6x blank minus 2 blank squared, where I get to replace that h with a 0. So that'll be a 0 there, and likewise there'll be a 0 there, because I'm finding the limit as h goes to 0. Okay, and 0 times anything is going to be 0, so we get that our derivative is going to be equal to 1 minus 6x squared. All right, let's do a quick little recap on this. Given that f of x was equal to x minus 2x cubed, we were asked to find the derivative, f prime of x. So when you're asked to do that, make sure that you go back to our definition of derivatives, defined by this, the limit as h goes to 0 of f of x plus h minus f of x all over h. I know that there are shortcuts out there, and we will get to them, but for now, in this chapter, we're not allowed to use any of them. We have to use the definition of derivatives, which means we have to go back to this, the limit definition of derivatives. Okay, so make sure that you learn how to use this process. This is what I expect to see on the test. Okay, so you set up your limit, go back to your definition. Be very careful when you substitute your function for x plus h, and then again for x. And then remember, from this point forward, our goal is going to be to algebraically manipulate, find an equivalent statement, use our knowledge of algebra and arithmetic to simplify, cancel, reduce, get to a point where we can replace the h with a 0 and not divide by 0. If we can cancel out the h and get to a point where we just have a polynomial, we know from our work with limits that the limit of a polynomial is equivalent to evaluating that polynomial at the limit value. And if we have a rational function, then we know we're allowed to replace the variable with 0 in this case, as long as we're not dividing by 0. Okay, so be very careful, show your work, expand things, cancel things, reduce things, as we saw here. One of the nice algebraic properties we can use is to replace this statement of divide by h with a multiply by 1 over h. It kind of makes things a little nicer. Okay, so in our case, we were able to do all that, and we got to a point where we had a polynomial. And we know from limits that the limit of a polynomial is equivalent to just evaluating that polynomial at that specified value of our limit, in this case, 0. So we get to replace all those h's with a 0, and this is what we end up with. Okay, all right, so this is the derivative function of the original function. If we think about the domains, our original f of x function, f of x, is just a polynomial, so its domain is all real numbers. Right, capital R with an extra slash through it means all real numbers. Or we can also say negative infinity to positive infinity. And now its derivative function is again just a polynomial. Nothing weird here. Can't divide by 0, no even roots of negatives, nothing like that. So the domain again is all real numbers. Negative infinity, positive infinity. Okay, so let's graph both of these and see what it looks like. Okay, so this is a nice little applet where we get to punch in the function. The original function is here, x minus 2x cubed. This is what we worked with. And so that's this black function here. That's that one. And so what we're going to have here is the tangent line at various points. So this green line here is the tangent line. And if we think about the slope of that line, the slope of this line right now is a 1. That's what that little 1 dot right there is. As I start moving this around, then the tangent line is going to move. And what this applet is going to do is that it's going to keep track of the slope of the green line and continuously graph those pair points, to graph those slopes to give us ordered pairs. So for example, as I move this a little bit forward this way, the angle has decreased a little bit. It's still a positive slope. The green line still has a positive slope, but it's a little bit smaller. That's why this little dot appeared that's a little bit lower. And then this slope is still positive, but a little bit smaller. Still positive, but a little bit smaller. Still positive, but a little bit smaller, until it reaches a nice horizontal level. Well, it can't quite nail that horizontal level, but it reaches a horizontal level which is 0, and then it'll become negative. It's a negative slope, and then a bigger negative, bigger negative, bigger negative, bigger negative, bigger negative, bigger negative, right? And so that's what's happening in this direction. The slope is going infinitely big in this direction, right? It's never quite vertical, even though it's going to get infinitely close to being vertical, but not quite vertical because that would be undefined, right? In the other direction, okay, so we'll go back this way, we're going to get to 0 again, and then a small positive slope, and then bigger positive, bigger positive, bigger positive, bigger positive. Somewhere in the middle of this, we reach the highest positive slope we're going to get, and then it starts to become a smaller positive again, smaller positive, smaller positive, smaller positive, until again we reach 0. And then it'll cross over from a very small positive to a very small negative. Okay, and then it becomes a bigger negative, bigger negative, bigger negative, bigger negative, bigger negative, bigger. So again, going in this direction, we get bigger and bigger and bigger negative, infinitely large negative numbers, right? So remember that even though the value of the function here is a positive, the slope is negative, right? So that's why the function comes this way. Okay, so if we were going to do that continuously, add more and more dots, eventually we would get a pretty good idea of what the derivative function looks like. And this is exactly the equation we found. Negative 6x squared was what we found as the derivative of the function. So let's show it. Oh, sorry. 1 minus, so here's the derivative function, 1 minus 6x squared. And here is the function down here. So if f of x is equal to the square root of x plus 3, find the derivative of f of x. Okay, so again, this is another way that they can ask you to find the derivative. So let's begin by using our definition. F prime of x equals to the limit as h goes to 0, f of x plus h minus f of x, the whole thing divided by h. Okay, so the first function, f of x plus h, it's going to go right in here. We need to put an x plus h there. That would be this function, following those instructions. And the second one, well, it's just x, which just looks a little silly, like we're just copying it. So in here, we'll get an... Okay, and now how do we fix this? There's really not much we could do. We can't combine them. You can't just square them. So this is going to be one of those cases where we take advantage of conjugate pairs. So remember, let's put it in green. Remember that if we have a plus b times a minus b, they're identical binomials in every way, shape, and form except one has a plus, one has a minus. The order of the plus and minus doesn't matter. But we know that when we FOIL this, we get a squared minus ab plus ab minus b squared. The middle terms cancel, and what we have left over is an a squared minus a b squared, right? We call these difference of squares. So what's nice about difference of squares is that we know that if we want to factor them, they factor like that. Or if we want to multiply these things, we know they multiply like that. So we can kind of skip this middle step once we identify them. And that's what we want to take advantage of here. We want to multiply this by its conjugate pair. So it's going to be this identical thing with a plus in the middle because we already have the minus. So we're going to think of this as one giant fraction. So let's put a little 1 here. Anytime you want to convert anything into a fraction, we can just put a 1 underneath it. And now we're going to multiply the numerator and denominator by its conjugate pair. Okay, so now we are going to FOIL this numerator. And of course, we don't actually want to FOIL it. We want to take advantage of this. They're conjugate pairs. They're identical in every way, shape, and form, except one has a minus and one has a plus. So we know that they're going to turn out to be this form. It's going to be one of those, the first term squared minus the second term squared, always a minus, right? Even though we have a minus and a plus, when we FOIL them, we're going to end up with a minus, right? The last term is going to be this minus square root of x plus 3 times positive square root of x plus 3. So it's going to be a minus. Okay, so this will look like this. Okay, so the numerator turns into this. The denominator we're just going to leave alone. Okay, so we tuck it underneath there. We have one big happy fraction. And what's great about this is that now we have the square root of something squared. So we know that these two properties will undo each other, right? We take the square root of something and then we square it. Then this operation will reduce with that one. And this will undo with that one. They're inverse operations, releasing the value of our function. So this turns out to be the limit as h goes to 0 of 1 over h, a giant fraction where we'll have the x plus an h plus a 3. Be careful that this minus still applies to this whole thing. And this is where some stuff can cancel. So now we have positive x minus x. These two can cancel. And I have a plus 3 minus 3. These two can cancel. So in the numerator, the only thing that has survived is this h. Okay, positive h. I'm going to copy that again. And now this h can cancel with that h. And finally, we've arrived at something. Looks like this. Limit as h goes to 0 of 1 over square root of x plus h plus 3 plus square root of x plus 3. Okay, so at this point, you might think we took something that looked kind of ugly into something that looked just as ugly. So what have we really accomplished? But we've actually accomplished something very useful because we've achieved an equivalent form of our original statement such that now if we replace the h with a 0, we will not be dividing by 0, right? So this is a rational function. And if we replace the h with a 0, we don't divide by 0, therefore we're allowed to do it. The value of this, the result of this limit is equal to the value of this rational function evaluated at h equals to 0. So we're going to go ahead and do that. The derivative then is equal to giant fraction 1 over x plus blank plus 3 plus the square root of x plus 3. Okay, so now all I have to do is take that 0 from there and put it there. That's where that comes from. The h used to be a 0. And so now what we get is x plus 3, right, since that's just a 0, plus another copy of x plus 3. And since they're both identical, square root of x plus 3, square root of x plus 3, I have two copies of square root of x plus 3, so I can combine them. And so I end up with 1 over 2 square root of x plus 3. That's my final answer. Okay, so if the original function f of x is the square root of x plus 3, let's think about the domain. The domain of the square root function, because it's an even root, we want to make sure that whatever's inside that denominator is not 0. Is not negative. So we need to set up x plus 3 to be strictly greater than 0. If we subtract 3 from both sides, we get that x must be strictly greater than negative 3. And so that's the domain for the original function. So f of x has a domain of x must be strictly greater than negative 3. Well, in fact, greater than or equal to, right? We're allowed to have a 0. Square root of 0 is 0. So this should be greater than or equal to negative 3, which means this should be greater than or equal to negative 3. Or we can rewrite it as bracket negative 3 up through positive infinity. Okay. A quick little check would be good. So if we replace x with a negative 3, we get square root of 0. That's okay. The answer is 0. If we replace the x with a 0, then we get square root of 3. That's a valid answer. And so on and so forth, right? So those are all good. Okay, what about this one, right? So we got two things to avoid that we want to avoid. Number one, we want to avoid taking the even root of a negative number. Okay, so that will accomplish it by using this set. Except we also have to make sure that we don't divide by 0. So for the case of the derivative, we don't want the negative 3 to be an option. So the domain of f as a domain, it's going to be just x is strictly greater than negative 3, or negative 3 up through infinity, right? So there's only a very subtle difference between both of their domains, and that's really this bracket, right? That negative 3 is allowed to be a value of the original function. However, in the derivative, negative 3 is not a valid result, right? If we try and plug in a negative 3 into here, we're going to get an undefined. Okay, so again, quick little recap. We were given our function, and we were asked to find the derivative of our function. Always begin by setting up the definition, the limit definition of a derivative, right? So you should have this memorized. And then we begin by very carefully replacing the function by an argument of x plus h for the first part of it, f of x plus h, right? And then minus the second one. And be very careful that this minus applies to everything. And then it's algebra. Depending on the actual equation, there's a variety of algebra tricks we can employ to make this work out. So it might be as simple as combining fractions. It might be something where we have to do this, multiplied by its conjugate. It might be something where we have to rationalize something. So there's a variety of tricks that we have to employ. But our goal is always the same. We want to manipulate it algebraically to come up with equivalent statements, right? This whole thing is equivalent to 1. I've multiplied this by a version of 1, so I haven't changed anything. So this is equivalent to this, which is equivalent to that, which is equivalent to that. And so we manipulate and find equivalent versions of our original statement, and we want to get to a point where we can replace the h with a 0 and not be dividing by 0. Okay, so that's what we ended up with. Okay, let's graph these. Okay, coming back to this app, I've punched in here our function value. It was the square root of x plus 3. So in this equation, we have to type in, or in this applet, we have to type in sqrt to represent the square root. So sqrt of x plus 3 is the square root of x plus 3 was our original function. Here it is in black. That's what it looks like. So it's going to be our standard square root function that's been shifted to the left by 3 units, if you remember your section on transformations. Okay, so at this point here, the tangent line is this green one, and we can see it's got a positive slope. Okay, so that's what this little dot here represents. It's the value of the slope of the line tangent there at this point. Okay, so now if I move it a little bit to the left, what's happening to that slope? That slope is getting bigger and bigger and bigger, always positive, right? It's getting steeper and steeper and steeper. And so you see what's happening with the value of our derivative. They're getting bigger and bigger and bigger in the positive direction. So as we go this way, like this, now the angle is much bigger. That's why this little green line is getting bigger. As I go bigger, bigger this way, a little bit more, a little bit more, a little bit more. See, the angle is still positive, and it's a much steeper positive angle. That's why this is climbing. Okay, I go more and more and more and more and more and more. It gets more and more and more steep, right? More and more steep. So it's easy to see where this is heading. This is getting infinitely close to a vertical line, but it's never going to quite reach a vertical line. It's just okay. But then if we go in the other direction, we see that the slope is still positive, getting a little bit smaller, right? The angle is becoming less steep, it's still positive, and then less steep and less steep, still positive, right? As we can see, if we travel this way, the slope of this tangent line is never going to be horizontal, so it's never going to be 0, and it's never going to go in the other direction, so it's never going to be negative. So it's just going to be positives all the way through, and they're just getting smaller and smaller and smaller, right? It's getting less and less steep as we see. That means that this, the derivative function, is going to get closer and closer and closer and closer to 0, right? It's approaching a horizontal line, getting infinitely close to a horizontal line, but never quite reaching it. Okay, so that's what the derivative function looks like. And then we can just have this program give it to us, and here it is. Okay, so here's the derivative we found. We know that this is equivalent to what we found, right? Because we just put the 2 out in front. So this will be 1 over 2 square root of x plus 3. Okay, so this is the derivative of that function, and its graph looks like this. As I go through, I can trace it out. Again, the slopes are always positive. That's what's interesting about this graph. The tangent line has always positive slopes. So that means that its f of x function is always, that means that its derivative function is always going to be above the x-axis. Over here is where the interesting things happen in this little tail, because the slopes become very big positive angles, very big positive slopes in this direction. And as you can see, they shoot off to infinity. This line here becomes infinitely close to becoming vertical, but never quite gets to exactly vertical in this way. And then in the other direction, it gets infinitely close to becoming horizontal, but never quite reaches horizontal, right? The underlying function f of x is always growing, even if it's growing quite slowly. Okay, find f prime of x if f of x is equal to 3 plus x divided by 2 minus x. Okay, so another way that they can ask you to do the exact same thing we've been doing, find the derivative. So, as we know by now, we need to start by using our definition, our limit definition of derivatives. Okay, so the derivative is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So now I'm going to take advantage of some notation. I'm going to move this over so we get this. So all I did is rewrite this statement of divide by h as multiply by 1 over h, right? Same thing. Okay, so now I'm going to very carefully replace my input variable here with an x plus h and, well, copy it again because it'll be just an x for the second part. Okay, so here is my input variable into the first function. Following the instructions, here's the f of x function. These are the instructions. So that means I gotta do 3 plus blank divided by 2 minus blank. And in this case, that blank is going to be an x plus h and an x plus h. Over here, for the second function, well, it's just going to be the variable x. Seems a little weird. We're just going to end up copying it. It turns into an x there and an x there. So we get x and x there. Okay, so that's how we translate that. And now we try and simplify this. So there's not much to simplify. Maybe distribute this minus. And that's about it. So we're going to have to do something pretty quickly here. Limit as h goes to 0 of 1 over h, 3 plus x plus h divided by 2 minus x minus h minus 3 plus x over 2 minus x. Okay, so what I'm going to do now is going to try and combine these two separate fractions by rewriting them in a way that gives me one simple big fraction. I'm going to multiply the numerator and denominator of this fraction by 2 minus x, and I'm going to multiply this fraction, numerator and denominator, by this, 2 minus x minus h, and then I'll have two fractions that have the exact same denominator, so I'll be able to combine them. Okay, so now we're going to have to FOIL these guys, and then we get to bring it all under one big happy fraction with the product of these two in the denominator. So let me copy that. Okay, so now we have one big happy fraction. Okay, so we're going to have to FOIL these. When we FOIL these, we get the following. Okay, so foiling these means I'm going to multiply 2 by all of these. So I'll get a 6 plus a 2x plus a 2h. And then I also have to multiply minus x by all of these. So minus 3x minus x squared minus xh. And then combine them. And these two will combine, and nothing else will combine, really. So we get a minus x squared from there. Takes care of that guy. And then these two combine, Positive 2x minus 3x gives me a minus x. It takes care of those. Then I get a plus 2h minus xh plus 6. Okay, foiling these guys over here, I multiply everything by 3. So I'll get a 6 minus 3x minus 3h. And then I multiply everything by x. So I get a 2x, so plus 2x minus x squared, and then minus xh. So when I add them together, I get a minus x squared. Takes care of that. And then these two combine to give me a minus x. Takes care of that. And then nothing else really combines, so I end up with a minus 3h minus xh plus 6. Okay, and that's how we FOIL these. Be real careful that this subtraction still applies to all of that over there. So let's be careful when we copy that down. Okay, so be very careful in the way that we translate that. So this, well, let's not put it there. This is what goes right in here. And then this is what goes right in here. Be careful with all those signs. And remember that there's a subtraction there, so we're still going to have to distribute this subtraction, simplify it, and then cancel. Get rid of those things. Okay, so now let's go ahead and distribute that minus and see what we get. Okay, so if we pay attention to the distribution of this sign, we end up with a minus minus, we end up with a plus x squared, and then a minus minus, we get a plus x, and then a minus minus, we get a plus 3h, and then minus minus, we get another plus xh, and then finally minus plus, we get a minus 6. Okay, so let's zoom back over here. Okay, now this is the fun part. A bunch of stuff will cancel. So let's go over here. The minus x squared cancels with a plus x squared. And the minus x cancels with the plus x. And the minus xh cancels with the plus xh. And plus 6 cancels with minus 6. And so the only things that survive cancellations are going to be this guy and this guy, which combine. We have a 2h and a 3h combined to 5h. So this reduces to so combining those two, we get as 5h. And now these two cancel. H cancels with an h. And so we get f prime of x equals to the limit as h goes to 0 of this 5 over 2 minus x minus h, 2 minus x. And now we've achieved, we've gotten to a point where if we replace the h with a 0, we won't be dividing by 0, right? It's a rational function. And we know from our work with limits that if we want to find this limit, we have the limit of a rational function is equal to the value of that rational function evaluated at that value for the limit. So we can just replace the h with a 0. So this is going to become 5, 2 minus x minus 0, 2 minus x. So we replace the h with a 0, and when we do that, we end up with 2 minus x times 2 minus x, which then becomes 5 over 2 minus x squared. Okay, so that'll be our derivative. Okay, so if the function given is f of x equals to this rational function, 3 plus x divided by 2 minus x, and you're asked to find the derivative, go back to the definition, the limit definition of derivative. So here it is, and then be very careful with our substitution so that we can evaluate the function, the given function at x plus h, and then subtract off the given function evaluated at x. Remember, our goal is now to do something to manipulate this in a way so that we can find the limit. We want to simplify it, cancel it, reduce it, multiply by conjugates. We want to combine fractions. We want to do whatever it takes to get to a point where if we replace the h with a 0, we will not be dividing by 0, right? We always start off with an h in the denominator by the definition, so we're always going to start off with that as a problem. If we replace the h with a 0, we're going to be dividing by 0. So in this case, the trick was to just combine both fractions under one big happy fraction, and then as long as we're really careful about how we FOIL things and how we distribute signs, then a bunch of stuff will cancel, reduce, and we end up with a situation where if we replace the h with a 0, then we will not be dividing by 0, and then that's our answer. Okay, so this is the equation of the derivative function, f prime of x, given this as our function. Let's think about our domain. Our domain for this function here, the domain is, well, you can plug in anything you want as long as you don't accidentally divide by 0. So positive 2 is the only problem, right? So the domain for this one, the domain of our original function is going to be all real numbers except 2. So all reals except 2, right? We can also express that by negative infinity up through 2 union 2 up through positive infinity. Right, so the only thing that's missing here is that positive 2. And for our derivative function, well, it's the same thing. We can't divide by 0, so we can't input the same value. So it's going to be the exact same domain. Same domain as f of x. They share the same domain in this case. All real numbers except don't let x equal to positive 2. Okay, let's graph it. Okay, so back to this applet. Here is our original function, f of x equals to 3 plus x in the numerator divided by 2 minus x in the denominator. That's this black one here. And it doesn't do a very good job, but we know that there's a vertical asymptote right here at x equals to 2, right? X equals to 2 is not a valid member of the domain of this function. And we can see that the limit as x approaches 2 from the left-hand side, the function will go toward positive infinity. And we can see from our graph the limit as x approaches 2 from the right-hand side, our function will approach negative infinity. There's a vertical asymptote here. Okay, so now the slopes of the line tangent. At this point right here, at this tangent, at this point on the original function, this tangent line green has a positive slope of about 1. And then as I move toward the right, then I stay with a positive slope. It's always a positive slope, but that positive slope is getting bigger and 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 bigger, right? And if I move in the other direction, then it's still a positive slope. It's just getting smaller and smaller and smaller and smaller and smaller. It's getting closer and closer to a horizontal line. It's never quite horizontal, but it's getting closer and closer to horizontal. The green line is never negative, right? It's never horizontal, it's never negative. So that means that the slopes are always positive. that means that the graph of the derivative will always be above the x-axis for this zone. Okay, so it's going to be really close to 0 around there, but not quite 0. And then going in this direction is just shooting off toward positive infinity. That slope is getting infinitely large in the positive direction. On the other side over here, we see that the slope is positive there, and it's approaching horizontal in this direction. In this direction, it's approaching horizontal, but not quite. It's not quite horizontal ever. So it's always going to be a very, very small positive slope. And then as we go this way, it still maintains a positive slope. Notice that the actual function values are all negative down here, so that gets a little confusing, right? If I think about the output of my function f of x in this range, we see that it comes down here and becomes a negative output value of the function, but the slope tangent is still positive. So all these slopes are positive, and now if I move this way, the slopes are becoming infinitely large in the positive direction, right? These are all very large positive slopes coming all the way down into here. And so we see that as I continue to graph more and more points, so I can see that as I continue to graph more and more and more and more points, eventually the graph of the derivative looks like this. Okay, so now if I just show what that derivative is, it looks like that. So this one is the graph of the derivative, and it's equal to this. The derivative is 5 over, and this is 2 minus x squared. That's what this is. Okay, other notations to derivatives. Okay, notation is a really big part of calculus. Remember that nobody sat down and invented the whole thing from start to finish. It was a combination of work from lots of different people. Some of these people never met each other. Some of these people didn't speak the same language. And in many cases, they didn't even really know that they were collaborating with each other. They were just kind of working on their own little individual niche thing. And it wasn't until later when Newton came along and said, hey, wait a minute, all these pieces of math actually come together, and he brought it all together. But we still have this residual effect of having lots of different notations that mean the same thing, and we keep them because in certain parts of your book, one notational style will make a lot more sense. It'll kind of be smooth through the process of doing your symbolic manipulation to get from your question to your answer. But in some chapters, one notation style is better than another. This is just like, for example, if we had y equals to 3x plus 2, we learned how to write equations this way. But then later we used function notation, and we learned that, we could actually write it as f of x equals to 3x plus 2. Same thing, except that this has some advantages to it. If we wanted to evaluate things, like if we wanted to find f of 7, then we know that this means that if we replace the x with a 7, we'll find our answer. So that'll be 21 plus 2 is 23. F of 7 equals to 23. If we keep this style of notation and we replace the x with a 7, then we get the same answer, but we do lose a little bit of information, right? If we just present to someone y equals to 23, we lose the fact that the input value was a 7. Whereas in this style of notation, we keep both the input value of 7 and the output value of 23. So that's the nice advantage of this. The advantage of this is that if we wanted to solve for y, it makes it a little less cumbersome, right? We can subtract. We can say y equals to 3x plus 2. Subtract 2, divide by 3, we get y minus 2 divided by 3. Over here, we could do the same thing, but it's a little bit more cumbersome. 3x plus 2, we can subtract 2, divide by 3, get f of x minus 2 over 3 equals to x. But now that looks weird for people. And then there's more advantages. Any rate, there's two different ways in which we can express this equation. So likewise, there's different ways in which we can express derivatives. So sticking to this style over here, let me erase this stuff. We don't need it right now. Just pointing out that there were different ways in which we can express a linear equation. Okay, so sticking to this style, one way of saying find the derivative, find the derivative, well, we could say y prime, right? That little prime there means it's the derivative of the y function. Likewise over here, well, we could also say f prime of x, same thing, find the derivative of the function, okay? Another thing we could say is to say d dx, derivative with respect to x of the y. And we could do the same thing over here, the derivative with respect to x of f of x, like that. And sometimes they don't even put the parentheses, so they could just say d dx of f of x. And sometimes they don't even put the x, so you might see it this way, d dx of f, right? Those all mean the same thing. Find the derivative of the f function. Likewise over here, sometimes they put the parentheses, sometimes they don't. d dx y, where the y is kind of large like that. And sometimes they make it small and kind of tuck it up here, so it ends up looking like this, dy dx. Okay, same thing. These are all different ways of saying derivative. A couple other ones is to say, let's put a giant D in front of the f of x. That's another way of saying find the derivative of f of x. And then keeping true to this, so making sure that people understand that it's the derivative with respect to x. Another thing we could do is just put a little x there of f of x. These all represent ways in which you will be asked to find the derivative. Okay, I think I covered most of them. Also keep in mind that for this last one, dy dx, that this is equal to the limit as delta x goes to 0 of delta y over delta x. Okay, we saw something like this before. Okay, definition. A function f is differentiable at a if f prime of a exists. It is differentiable on an open interval from a to b, or from a to infinity, or from negative infinity a, or from negative infinity to positive infinity, if it is differentiable at every number in the interval. Okay, so we have our definition for a specific point a, and then we could say that it's differentiable on an open interval if it's true that any point you choose in that interval will result in a case where f prime of that number exists. Okay, let's look at an example. Okay, let's explore this question. Where is f of x equal to the absolute value of x differentiable? Okay, so let me, in fact, make this one a little bit thicker so that it's clear that this is the absolute value function here. Okay, so when is this differentiable? For what values in the domain is it differentiable? Well, first of all, the domain of this function is all real numbers. All real numbers, right? I can plug in any number I want, and I'm not going to violate any rules. I'm not going to be dividing by 0. You can put in negatives, positives, 0. It's all going to be okay. So the domain is all real numbers. So let's break it up into pieces. So first of all, let's think about the case where, it'll be case 1 when x is greater than 0. And then case 2 is going to be, well, what about when x is strictly less than 0? And then case 3 is going to be, well, what if x is exactly equal to 0? Between these three cases, we will cover everything in the real number set, right? So we're going to cover case 1 first. Let's think about that one. Case 1. Case 1, x is strictly greater than 0. So if it's strictly greater than 0, we're saying it's positive. So note that if x is strictly greater than 0, it's definitely positive, then f of x equal to the absolute value of x, well, it's just going to be equal to x. That's what happens when we input a positive number, right? Strictly greater than 0 means that x is always positive. X is always always positive. So if we're sticking just to the cases where we input a positive number, well, then it doesn't really make a difference at all. It's just going to be x, right? Okay, so let's figure out the derivative. So let's write down our definition. Okay, so the derivative is going to be equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, so now let's think about this. So we've already pointed out that the absolute value of x, in the case where x is strictly greater than 0, it's definitely positive. Well, this is just going to be x, right? So we can get rid of the absolute values. What about this one? Well, notice that h is an unrestricted limit here. It goes towards 0 in either direction, but it's getting infinitely close to 0. Okay, so because it's a number getting infinitely close to 0, and h is never actually 0, then we have to use the fact that the number system is dense. What does that mean? So let's say here's my number system, and here is 0. If x is chosen to be any positive number that's not 0, even if it's really, really, really close, like I choose x to be right there, there's an infinite of numbers in that little gap right between the 0 and the x. And if I get even closer, that's okay, just zoom in, right? No matter how close it's written, there's still an infinite number of values between those two, right? So if we have 0 and then x is equal to 0.000000001, that's okay. Between these two numbers, there's an infinite number of numbers, okay? So there's always going to be a little gap there between the two. So for that purpose, I can always zoom in, and then just redraw it this way. So for all intents and purposes, it could just be drawn like that. Even though this is infinitely close to there, I've just zoomed in like 1,000 times, and that's why I see this. Okay, so no matter how close it is, there's a little gap there. And on the other hand, h is approaching 0, right? And so if I'm going to go plus h, right, if h is, okay, so let me put x, this is the x number line. Now let me think about the h number line. H is approaching 0, so here is 0. Now h can go from either direction, a small, very, very small negative, or a very, very small positive number. If it's a positive number, then x plus h will be some value over here, x plus h. And if it happens to be that h is negative, then we'll have an x plus h be on the left side, x plus h, because the h might be a negative number, so it might be to the left of it. If h is big enough, then yes, that x plus h might be over here on the negatives. X plus h might turn out to be over here. But keeping in mind that we don't care about one specific number, we care about the limit as h goes to 0. So even if for some specified value of h that might be relatively large, eventually those h values are going to approach 0. They're going to get infinitely close to 0. And so eventually we'll get to a place where they're on the positive side, so we don't have to go to the negatives. And so we will end up with x plus h being positive, right? It'll be somewhere near the vicinity of x. Good? Okay, and so we can conclude, the whole point of this is to conclude that there exists, no matter how small h, let me write it down. No matter how small x is, no matter how small x is, there will always be an h small enough. There will always be an h, positive or negative, small enough so that x plus h is still positive. Right? Remember, this whole thing is for the case where x is some small positive number. For example, x could be 0.01, small positive, right? And now h is approaching 0. Maybe the first value of h is negative 0.5. You're like, oh, but if I add those, I go to the negatives. That's okay. H is approaching 0. It's going to get closer to 0. Eventually, h is going to become such a small positive or negative, 0.00000001, that when you add x plus h, it's still going to stay positive. Okay, so keeping in mind that we have the limit as h goes to 0, then for some value of h, eventually this h will become so infinitely close to 0 on either side of 0 that this stays positive. And what's the point of that? The absolute value of something positive is going to be positive. Okay, so that's what we want to conclude here. Let's erase this. So the limit as h goes to 0, for some value of h, eventually this turns into the limit as h goes to 0 of, and then we can just get rid of those absolute values. This becomes x plus h minus x all over h. Now the x's cancel, and we're left with an h over an h. F prime of x equals to the limit as h goes to 0 of h over h. Remember that we don't actually ever let the h equal to 0. We want to get infinitely close to 0, but never actually equal to 0. So we're not really dividing by 0. These things cancel. They become 1. And so that's what our derivative is going to be. This whole thing just equals to positive 1. So the derivative is always going to be positive 1 when x is positive. That takes care of case 1. Okay, so now we're going to go to case 2, the case when it's always negative. Case 2, x is less than 0. In other words, x is always negative. Okay, so just like before, we're going to set up our limit. So the derivative with respect to x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. X prime of x is equal to the limit as h approaches to 0 of Okay, so now in this case, in this scenario, case 2, we're only considering the cases where the x is definitely a negative number. So note that when we know that x is definitely a negative number, then if we have the absolute value of x and we know x is negative, and we know the absolute value makes everything positive, then we know this is going to be equal to x times, and we have to introduce a new term of negative 1 because we know x is negative. So for example, if this was negative 3, we know the absolute value of negative 3 is going to be positive 3. So the way we do that is by copying that number in there, right? Whatever's in there, just copy it again, but multiply it by an extra term of negative 1. That's going to make it positive. Right? So that's how we get that the absolute value of negative 3 becomes positive 3. Okay? That's the really tricky thing here. We have to introduce an extra negative 1 when we are guaranteed that whatever is inside there is negative. Okay? If we don't know whether it's positive or negative, then it's hard to make a conclusion. Right? So we have to separate it into cases where we know it's absolutely positive, leave it alone, it's equal to x, or the cases where we know for sure it's definitely negative. Okay, so it's definitely negative. We can get rid of the absolute values and introduce this new term of negative 1. Okay? All right, and likewise, just like before, we know that x is going to be some negative number, and no matter how close it gets to 0, there will always be an infinite set of values between that number and 0. So here is the number line for x. Here is 0, and no matter how close to 0 x is, even if it's incredibly close, like right there, here's x, incredibly close to 0, but negative, that tiny little gap there, I can always zoom in, zoom in, zoom in, zoom in, and in that tiny little gap right there from x to 0, a whole infinite number of values can live right in there, right? So for the purposes of drawing it here, I'm just going to draw it way out here and just assume that this means I've zoomed in a lot, right? This is actually incredibly, incredibly close to 0, but negative, and I've just zoomed in so much that this little gap exists. Okay, so no matter how close it is, there's always a gap, and if we keep in mind that h is going to be a number that approaches 0 from either side of 0, so now let's think about the h once again. So here is the number line for h, and here's 0 for h. So h is a value that's approaching 0, and it's approaching it from either side. So maybe that's h, maybe that's h, maybe that's h, maybe that's h. Right? It could be anything, but it's getting infinitely close to 0. So for some specific value of h, just 1, it might be large enough to where when we add x plus h, it might cross over onto the positive side. It might go way over there, right? Like, for example, just to throw some numbers down, again, maybe x is negative 0.01, but maybe h is equal to 0.7. So when we add negative 0.01 plus 0.7, we cross over the 0 to the other side, and now it becomes positive. Okay, let's not panic. Remember that h is not a specific number. H is approaching 0. It's not going to stop at 0.7. It's going to go to 0.2, 0.01, 0.001. And it's also going to go into the negatives, right? It approaches 0 from both sides. So eventually there will be a value of h so small, so tiny, that when we add it to here, x plus h is still going to stay in the negative side. X plus h is still going to stay there. Now, of course, it might be that h itself is a negative, so when we add a negative plus a negative, we go deeper into the negative. So it might be that x plus h might be over here, deeper onto the negatives. Either way, our point is going to be that as h goes to 0, there exists an h so small that x plus h is still negative. Given that x is negative, there exists an h so small that x plus h, right, the addition of the two, is still negative. Right? So the limit as h goes to 0, eventually, at some point, as I'm approaching 0, there's going to be a value so small that beyond that point, not just at that point, but beyond that point, x plus h is always negative. Okay? So there is a point where I can conclude this is going to be negative for that specific value beyond x plus h is always negative, and so we can get rid of the absolute values by saying it's going to be this negative number, and then we introduce a new multiple of negative 1. So this is going to be rewritten this way. F prime of x is equal to the limit as h approaches to 0 of is going to be x plus h, and I know that this is going to be negative, so I have to introduce a new factor of negative 1. That makes it positive. Minus, and then here I'm guaranteed x is negative. The absolute value of a negative number is going to be that same number times a new factor of negative 1. That, and the whole thing gets divided by h. Okay, so let's simplify that. Let's distribute. We get minus x minus h plus x. F prime of x equals to the limit as h approaches to 0. And we get minus x minus h plus x all over h. Now the minus x minus plus x cancel. and I'm left with a minus h over a positive h, which just gives you negative 1. Okay, so now let's think of the case where x is exactly equal to 0. What is that going to be? So f prime of x, well, now it's not really a variable. It's just going to be equal to 0. So we can just erase this part here and say it's f of 0 is equal to the limit as h approaches to 0 of f of x, whoops, not x, of 0 plus h minus f of 0 all over h. Okay, so there's going to be f prime at 0 is equal to the limit as h approaches to 0 of, and then I'll have absolute value of 1, absolute value of the other. So this is going to be 0 plus h here, 0 plus h, and this is just going to be 0. And we know the absolute value of 0 is just 0, right? This isn't even a variable, it's just 0. So that's just going to go away. And then 0 plus h is just h. So this is going to become f prime of 0 equals to the limit as h approaches to 0 of the absolute value of h. Right? This is a minus 0, so that goes away. Absolute value of h over h. Okay, so now keep in mind that h is a number approaching 0, but this is not restricted to one side. It can go towards 0 in either direction. Right? If we think about the h line, here's h, here's 0. H is heading towards 0, but it can go there, it could go there, right? All these values can represent h as they get infinitely close to 0. And we know that when h happens to be positive, the absolute value of h will be h. And when h is negative, the absolute value will be negative. So this is not going to have any specific number. So let's break this down to the left limit and the right limit, since it's not super clear what it is this way. So if we break this down into pieces and think about the limit, let's break this down into pieces and think about the limit as h approaches to 0 from the right-hand side of h over h, where this is the absolute value of h. So if h is approaching 0 from the right-hand side, here I'm guaranteeing that h is always going to be positive. If h is always going to be positive, then that means that this limit is equal to just h over h, which cancels out to give me positive 1. Right? That's when h approaches 0 from the right-hand side. On the other hand, the limit as h approaches to 0 from the left-hand side, meaning it's always negative, it's going to be h over h, and then there's an absolute value there. So it's the absolute value of h divided by h, where h is guaranteed to be a negative. If h is guaranteed to be a negative, that means that this limit approaches to 0 from the left-hand side is going to be h, and this is where we have to introduce that extra minus 1. Right? I'm guaranteed that h is a negative number, so the absolute value of the negative number is going to be that number multiplied by negative 1. So in this case, the two h's cancel, giving me negative 1. So the right limit of this function exists, it equals to positive 1. The left limit of this function exists, it's equal to negative 1. So because the two limits do not match, that means that this limit does not exist, right? The unrestricted limit does not exist. So that's what we conclude for the case when when x equals to exactly 0. Okay, so let's recap. Given the absolute function, the function f of x equals to the absolute value of x, and we're asked to establish when is this function differentiable. We can see that the domain of this function is all real numbers, right? We can always plug in any real number into the absolute value function, and we get a valid result. So to figure out when it's differentiable, I broke it up into 3 separate cases. Case 1, this case, is when x is definitely greater than 0, strictly greater than 0. That means it's a positive number. That's this case right here. Case when x is greater than 0. When x is greater than 0, strictly greater than 0, a positive number, we did our work and we found that the derivative is equal to 1, right? So the derivative equals 1 in this case. Okay, so now we look at the other case. What if x is strictly negative, always a negative number, strictly less than 0? We did our work and we figured out that in this case, the derivative is equal to -1. Always equals -1 whenever we pick a value in that segment, right? This is the case 2, when x is strictly less than 0. And then we look at the case when x is exactly equal to 0. That's this case over here. So we set up our limit, and we get to this stage, the limit as h goes to 0 of this. So then we had to break it up into 2 separate limits. So here is the unrestricted limit. H goes to 0 from either direction. So we said, let's think about it approaching 0 from the right side. Let's think of it as approaching 0 from the left side. And we see that from one side it equals to 1. From the other side it equals to -1. So this limit does not exist. Okay, so let's recap the whole thing right here. Okay, so we can write the derivative function this way. F prime of x equals to 1, positive 1, if x is greater than 0, strictly greater than 0, and that it's equal to -1 if x is strictly less than 0. Notice that equal to 0 is missing. Usually, by default, if it's not written there, it means it's not part of the domain, and it does not exist. It might be written off to the side somewhere, so like maybe up here they might write f prime of 0 equals 2 does not exist to really make it crystal clear, but you should know that since 0 is not part of this domain here, it's not described, then that means that it does not exist. So we can describe the domain of this derivative function. So the domain is all real numbers, except x equals to 0. And we can also express it this way, -infinity to 0, union with 0 to positive infinity. Okay, so the domain of the original function was all real numbers. The domain of the derivative function is -infinity to 0, union 0 to infinity, all real numbers except x equals to 0. The function does not exist there. So f of x equals to the absolute value of x. Where is it differentiable? The domain is all real numbers. We broke it up into separate little cases. We found out that the derivative, it does not exist when x equals to 0. The derivative equals to 1 when x is strictly greater than 0. The derivative equals to -1 when x is strictly less than 0. So the domain of the derivative function is going to be from -infinity to 0, union 0 to positive infinity, all real numbers except 0. Okay, let's take a look at this graph. Okay, I'm back with this same applet. The absolute value of x is written this way, abs parentheses x. This is the absolute value of x. And its graph is going to be this V-shaped graph here, this V shape. So if we input 3, the output is 3. If we input 4, the output is 4. So this side is the positive portion of the line y equals to x. On the other hand, if we input a -2, the output is positive 2. If we input a -5, the output is positive 5. That's why this portion here describes what happens when we input negative numbers. So this is a portion of the line y equals to -x. Okay, for negative input values. Okay, so now the slope of the line tangent. So here we have this point on our f of x function, and its tangent is going to be this green one. and its slope equals to 1. And as I move anywhere along that, well, the slope is always equal to 1. It doesn't matter where you are. In fact, this is a case where the tangent line is exactly equal to the function, right? The green line is on the black line here. Right? This is one of those cases. So the slope is always equal to 1 as long as you're on the positive side. And when you skip on over to the other side, all of a sudden the slope is always negative 1. Always negative 1. No matter where you go, the tangent line is always negative 1. So as I go everywhere, we see that the green and the red begin to form the graph of the derivative function, which was this, very simply, that if x is a positive number, the derivative is going to be positive 1. If x is a negative number, its derivative is going to be equal to negative 1. And what happens at 0, as I put this over here, right at 0, there is no tangent line, right? If you think about the green or the red, what would it look like right at that tip, right? Where would it be? There's no way to really know exactly what that tangent line would be at that sharp little corner, and so it doesn't exist there. So that's a clue we're going to build on in a little bit. When we have a sharp corner like this, there's no way to really think about what the derivative would look like. Okay, all right, so now if we just ask it to graph it, we get this. And so here is the graph. Okay, and well, it wrote our derivative this way. But we prefer to write it the other way of 1 and negative 1 to really spell out what it means. Okay, so ignore this. So this is equivalent to what we wrote. So it's equivalent to writing it this way, right? I prefer this way because I think it makes it a little bit more clear, but the that little applet left it in a slightly different form. Okay, let's move on. All right, let's take a look at theorem 4. If f is differentiable at a, then f is continuous at a. This is a very popular theorem in calculus. We're going to spend a little time with it. So if-then statements, right? If this is true, then this is true. The reverse is not necessarily true, so keep that in mind. We'll revisit that again after I finish proving this, but let's talk about the proof. So if this is true, then this is true. So let's find what this means. Let's define what this means. F is differentiable at a. So that means that f prime of a equals to the limit as h goes to 0 of f of x plus h minus f of x all over h, right? That's what it means for it to be differentiable at h. Okay, the other notation style, though, for this, right, I'll put or, is that f prime of a is equal to the limit as a approaches to x Okay, so the other interpretation of this, getting away from this h notation, is this one. Remember that this means that the limit as the limit as x approaches to a of f of x minus f of a all over x minus a. So this is by definition what it means for a function to be differentiable at a. On the other hand, what does it mean for a function to be continuous at a? So continuous at a means that the limit as x approaches to a of in order for it to be continuous at a, it means that the limit as x approaches to a on f of x equals to f of a. Okay, let's do a little picture to kind of refresh our memories of what all this means. So for instance, if I had some function like this, and I had some value a, and so now the limit as x approaches to a, so here's some x value, here's some other x value, I'm getting closer and closer, closer and closer, closer and closer, closer and closer to a. the limit as x approaches to a of my function f of x, so this is f of x. Well, in this little picture, I can see that my a is, say, reaching to that point right there. So the limit as x approaches to a of my function, well, if it happens to be that when we evaluate the function at a, we get that exact same point, right? So if it turns out that this point is a comma f of a, right? So if it turns out that the limit, as we approach, as we get infinitely closer, as the input gets infinitely closer to a, the outputs get infinitely close to f of a from both directions. So that limit equals to that value. And if it turns out that the function is defined at a and it equals to the same result, then we have a case where it's continuous, right? What would it look like if it wasn't continuous? Well, the limit might approach that value there, but there might be like a little dot over here, and we might be asked to say that, oh, the actual value at a might be this little dot up here, so there might be like a little hole there, right? That would be a case where it wouldn't be continuous. But in order for it to be continuous, it must be that the limit exists as x approaches to a from both sides, and that limit is equal to the value of the function evaluated at a. Right? That's what it means for it to be continuous. And a little picture for the differentiable one. So remember that this one means that if we have some function, let's say that that function does that, and we have a tangent line like that, say at that point there, you can say that that point is equal to some value a. And so as x values are chosen, as x gets infinitely close to a from either direction, that's the limit as x approaches to a, then the ratio of f of x minus f of a all over x minus a is going to eventually, the limit as x approaches to a of this ratio is going to give you the slope of this line, right? That's the derivative. So slope, or the angle of that tangent line, slope of tangent line at point a comma f of a is f prime of a. The slope is f prime of a at point a comma f of a. Right? This is the point a comma f of a, and then the slope of that line is f prime of a. Okay, so just a little bit of review on what both of these two things mean. So if f is differentiable of a, that means that this is true. We have to show that this must be true. So we must show this in order for us to prove it. Okay, so to do that, let's begin by considering the following. Okay, so to show that f is continuous at a, we must show that the limit as x approaches to a of f of x equals to f of a. That's what we want to show. But we get to use the statement that we get to use that f is differentiable at a. That f is differentiable. So, as we saw before, that must mean that the definition of derivative is true. Okay, so note, this is kind of a hard place or difficult place to begin with, but we can say that f of x minus f of a is equal to f of x minus f of a. And then what we could do is we can multiply the numerator and denominator of this, right? Think of this as a fraction, and we can multiply it by x minus a over x minus a. Right? This is a new version of 1, as long as x is not equal to a. So this is valid as long as x is not, so valid if x does not equal to a. And that's okay. We're not going to let x equal to a. Okay, so then we can just rewrite that a little bit and say that this fx minus f of a is equal to f of x minus f of a all over x minus a times x minus a over here. So I just kind of tuck this underneath here. Good. Okay, so now we're going to take a limit. Let's do the limit as x approaches to a of the left-hand side, f of x minus f of a. And that's going to be equal to the limit of this, the limit as x approaches to a of, and this would be f of x minus f of a all over x minus a times x minus a which is going to be equal to, okay, from our work from limits, we know that if we take the limit of a product, we can separate it into two different limits. So this will be the limit as x approaches to a of f of x minus f of a all over x minus a times the limit as x approaches to a of x minus a. The limit as x approaches to a of f of x minus f of a. Okay, well, we know this exists. This is the definition of derivative. This is, by definition, equal to f prime of a. Or all of this, the limit as x approaches to a. This is exactly equal to the derivative. Whereas this, well, this is just going to be equal to 0. The limit as x approaches to a, as x gets infinitely close to a minus a, this whole thing gets infinitely close to 0. Okay, so we have the limit as x approaches to a of f of x minus f of a is equal to this. And, well, we were given that this exists. That's all that matters. We don't really care what the value is as long as it exists. It's some number, right? Given as some number, exists as some number. And some number times 0 is going to be equal to 0. So from all of this, we can just conclude that this equals 0. The limit as x approaches to a of f of x minus f of a equals 0. Okay, now how is that going to be useful? Let's come back over here. So all we need to establish is that this exists, right? We were given the derivative is valid at a. It exists for some number. It doesn't matter what that number is because any number times 0 is equal to 0. The only place where we might have an issue is if it turns out that this doesn't exist, because doesn't exist times 0 doesn't equal 0. But as long as it exists, it's some number times 0, we're going to get a 0. So all of this lets us conclude that this limit, as x approaches to a, of f of x minus f of a equals to 0. So let me copy that up here. Okay, so all that work lets us conclude that the limit as x approaches to a of the difference between f of x minus f of a equals to 0. All right, so now we're going to take that and kind of start over here, and we're going to say consider the limit as x approaches to a of f of x. This is equal to the limit as x approaches to a of f of x plus 0
right? Nothing wrong with adding an extra 0 on there. Plus 0 doesn't do anything. Okay, well, let's reevaluate that. Let's rewrite it as the limit as x approaches to a of f of x, and then instead of a plus 0, I can rewrite it as a minus f of a plus f of a. Like that. Good. Okay, so then we know from our work with limits that we can separate these two. So this becomes the limit as x approaches to a of f of x minus f of a plus the limit as x approaches to a of f of a, like that. And well, from right up here, from here, we see that this whole limit, the limit as x approaches to a of f of x minus f of a, we've already concluded that this is a 0. Plus this, the limit as x approaches to a of the function f of a, well, this is just some constant. Notice that there isn't even an x here. This is just going to be f of a. Right? Remember, that's kind of like the limit as x approaches to 7 of the function 5, right? It doesn't matter if we have y equals to 5 as our function. This is just a horizontal line. It doesn't matter what the input is. As the inputs approach 7, the outputs are always 5. So this is just 5. Same thing here. This is going to be some constant value a. So this just equals to f of a. And so we can bring it all together and say that this equals that, which means that the limit as x approaches to a of f of x equals that. The limit as x approaches to a of f of x equals that. The limit as x approaches to a of f of x equals that, which means that the limit as x approaches to a of f of x equals to f of a, and that, by definition, means that the function is continuous. It's customary to do a little box with a little slash when you're done. Okay, with the proof. All right, let's zoom out here. Take a look at the whole thing. Okay, so the theorem was if f is differentiable at a, then f is continuous at a, right? So here a is some constant value. Okay, so to show that f is continuous at a, we must show that the limit as x approaches to a of f of x equals to f of a. That's the definition of continuous. We get to use that f is differentiable at a. So there's a couple of ways in which we can write the fact that the function is differentiable. We can use the h notation or not. Okay, so we want to start off with f of x minus f of a is equal to f of x minus f of a times x minus a over x minus a. I know it's strange to start there, right? Proofs are very difficult in math. You know, who would have done this the first time? Well, it takes a lot of work to figure out where you should start and how you should start, and really it just comes down to practice. So don't worry about where it started so much. In this class, you're not really responsible for proving things. So at this stage in your math career, if you can at least follow along, it's more than enough at this stage. So I wouldn't ask you on a test, for example, to prove it or anything like that. So don't worry about that. Just try and follow along and see if it makes sense. And try not to ask yourself, well, how did they know to start there? Well, they're brilliant. That's why. You know, people way smarter than me figured this out. So I wouldn't have known to start there either. I've seen it before, and I know that that's how you started. It's one of those tricks. And as you've seen these proofs more and more and more, it'll start to kind of occur to you when something new is presented that you think, oh, okay, well, this might be a good place to start just because it worked before. But like I said, at this stage, you shouldn't worry too much about it, okay? So they happen to start here, f of x minus f of a. This is how we start this proof. And you know, I already worked through this whole process, and the whole point of all that was just to conclude that the limit as x approaches to a of f of x minus f of a equals 0. right? Kind of keep that in your back pocket. And now we kind of start a new sentence over here. We're going to use this. As you see in your math career, and we see more and more proofs, they get more and more involved. Sometimes you kind of have to go off and prove a little side thing that you later come back and use in your main proof. So be really organized with your work. Okay, so you might see this as on page 1 or something. This of your work. This might be page 1, or sometimes I box it up and put like a little star next to it. Maybe box it up and put little stars next to it. So then here, when I reference it and I go here, this is equal to 0, then I might go, oh, okay, well, because stars, right? Go back to their page 1 to figure out why this is true, right? So now when you move on to page 2 and you put it all nice and neat. Now, if you want to be really slick, then you put this on page 1. And then when you get to this, you say see back page or see page 7 or something of your work, so you can kind of reference it when you need it. Anyway, organizing is half the battle, so be really neat and organized in the way you do things. And so hopefully this makes sense. We've shown that the function is continuous at a. Okay, very important, however. Note that the converse of this is false. It is not true. So that is, there are functions that are continuous but are not differentiable. So if we are told a function is differentiable, we can conclude that that function must be continuous. But the reverse is not true. If we are told that a function is continuous, we cannot conclude that the function is differentiable. Okay, so differentiable implies continuous, but continuous does not imply differentiability. It might be, if you know something is continuous, it might be differentiable, it might not. As we've already seen in an example before, when we're looking at the absolute value function, the graph of the absolute value function is that V shape. That V shape is continuous. So we have a case of a function that is continuous, but it is not differentiable everywhere, particularly at x equals to 0. We saw that the function is defined at 0, it's continuous at 0, it's that V, it's the tip of that V, right? But it's not differentiable at 0. Okay, so that's very important in calculus. Differentiable implies continuous, continuous does not imply differentiable. Okay, so in a broader sense, how can we tell when a function is not differentiable? Well, sometimes we have equations. It'll be presented in the form of an equation, and then we have to decide, is that equation differentiable? That's a much harder question. For now, we're just going to stick to the graphs. So if the graph of a function is given, how can we tell that that graph is differentiable and the derivative is defined? So as we just saw with the absolute value function, the absolute value of x looks like this v, right? So it's got this sharp corner. It indicates that the tangent line is going to face a very sharp turn, right? There was always negatives. The tangents were always negative here, and then it abruptly changes to being positive at the flip of a point there. So that's the first clue. If the graph has a very sharp corner, then we know that it is not going to be differentiable at those sharp corners, right? We call them corners or kinks, not differentiable there. Okay. Additionally, the fact that theorem 4 gives another way of finding the function. Theorem 4 gives another way for a function not to have a derivative. It says that if f is not continuous at a, then f is not differentiable at a, right? So continuity is required, but it isn't always enough. But if you don't have even the basics that it's continuous, then it's definitely not differentiable. So if a function is not continuous, it is not differentiable. So whenever the function has like a jump, a discontinuity, then it is not differentiable. Also, if it has a vertical line, then the limit as x approaches to a of the derivative of the function at x is going to go toward infinity, meaning that, remember, this is the f prime of x is the derivative of the function, the slope of the line tangent is getting infinitely steep, and the absolute values here just mean that it's getting steep in the positive direction or the negative direction. So here's a graph of that. The slopes of these red tangent lines in this direction, they're going infinitely negative toward the negative infinity direction, and then over here they're going infinitely toward the positive. The slopes of these tangent lines here are becoming infinitely large in the positive direction as x approaches to a from either side. So there's a vertical asymptote there, and that will be a place where the graph is not differentiable. Okay. Also, it could be that the graph doesn't go off to infinity or anything, but it gets to a point where it has a vertical. There's at least a little segment there where it's vertical. So at that point, the line tangent will be vertical, and so that will be a place where the function is not differentiable. Okay, so we have a few cases where if we see the graph, we can tell right away. If there's a break, that means it's not differentiable there. That's easy, right? The function must be continuous in order for us to even have a chance of it being differentiable. It cannot go off to infinity, so it cannot have a vertical asymptote at a. If it has a vertical asymptote at a, then it's definitely not differentiable. So these two cases are a little bit harder because there isn't a break. It is continuous, but it has either a sharp point like that, or it comes down and creates a vertical part there. A little segment of the function is vertical, and so at that point, we also have a place where it is not differentiable. Okay, so in order for a function to be differentiable, it must be continuous, and it must have no kinks in it, and it must not have one of these vertical segments. Okay, no discontinuities, no sharp corners, no vertical asymptotes, and no segments that are vertical in order for the graph of a function to be differentiable at a point. Okay, higher derivatives. If f is a differentiable function, then its derivative f prime is also a function. So f prime, the derivative of the f function, may have a derivative of its own, right? So we can take the derivative of the derivative, which we call the second derivative, and notation varies. So we use the little prime to represent the first derivative. Well, we can use the little prime once again to see that it's the derivative of the derivative function, or we can put two little tick marks like this, tick, tick, to find the second derivative. Okay. The other notation style is to do this, d dx of dy dx. Remember, this is one of the ways in which we can represent the derivative of the function y. And so we're taking the second derivative. And then, again, we can combine those two this way. And this one's a little confusing because this does not mean to square it. Right? This little 2 here does not mean that we're squaring anything. It means that we're taking the second derivative. Okay. Yet another notation style is these little tick mark things. What we can also do is write down the 2 there so that to represent that it's a second derivative. But so that people don't confuse this with squaring, what we do is we put it around parentheses. Okay, so f with a little 2 around parentheses like that, that also means that we want to do the second derivative. And of course, we can also do f of x with a little 2 right in there to mean that it's the second derivative of the f function. Okay, for example, earlier we worked with this one. We had f of x equals to x minus 2x cubed. Okay, and we took the derivative. And the derivative, we did it the long way. So we said f prime of x equals to the limit as h approaches to 0, f of x plus h minus f of x all over h. And then we did a lot of awesome work, and we figured out that f prime of x was equal to 1 minus 6x squared, right? So that's the answer we got from before, after a whole bunch of work. Okay, so this is our f function, this is f prime function. Okay, so notation-wise, well, we could have also gone back over here and said y equals to x minus 2x cubed. So we can also say that y prime equals to 1 minus 6x squared. Okay. Also, we could say dx of y equals to 1 minus 6x squared. And sticking to this notation, well, we can also say that dx of x minus 2x cubed equals to 1 minus 6x squared. Squared. Right? So that's that same style of notation. Going back over here, we can also say dx of f equals to 1 minus 6x squared. We can also say df dx equals to 1 minus 6x squared. We could also say dx of f of x equals to 1 minus 6x squared. And then, of course, then we can replace the f of x with the actual function, which would then bring it back to this style of notation. At any rate, all of these are ways to represent the derivative of our function. And these were all the first derivative. So now we can say the second derivative. And the second derivative can be written this way. Second derivative could be written as ddx of f prime of x, right? So this is already a derivative. Or I could say ddx of dy dx, like that. That's another way of saying take the derivative of the derivative. We can also use these little tick mark things. So I could say that it is y prime prime, or I could say y double prime, like that. Same thing. These are all ways of saying take the second derivative. What else? Oh, and then as I said, the other way of doing this is to say put a little 2 like that and say do that. The second derivative of the function f of x. Okay, so I'm going to stick to, say, this kind for now. Take the derivative with respect to x of f prime of x. So this would be d dx of f prime of x. And as we saw above, that means this. So it'll be the same thing as saying d dx of 1 minus 6x squared. And now I want to take this derivative, the derivative of this function. Okay, well, that means that we want to apply our derivative function definition to this. Let g of x equal to 1 minus 6x squared. So let's let g of x represent 1 minus 6x squared, which we know is that first derivative, is equal to f prime of x, right? Let's just get rid of that for a second. So now the derivative of the g function, following our definition, is going to be equal to the limit as h goes to 0 of g of x plus h minus g of x all over h. That's the definition of the derivative. That's how we can find the derivative of this function. So now g prime of x is equal to the limit as h goes to 0 of 1 over h times g of x plus h. So it's going to be 1 minus 6 blank squared minus 1 minus 6 blank squared. And let's make sure that this function is minus that function. And all of that gets multiplied by 1 over h. So for the first function, it's x plus h. That's what goes right in here. And for the second one, an x goes in there. So we get that this is x plus h in there, and this is just x. Following along with our process, we get that this is the limit as h goes to 0 of 1 over h. And then if we FOIL that out, we end up with 1 minus 6 parentheses x squared plus 2xh plus h squared, close parentheses, minus, and now this is just going to be 1 minus 6x squared. Okay, so then we distribute, so we get g prime of x is equal to the limit as h goes to 0 of 1 over h, 1 minus 6x squared plus, minus 12xh minus 6h squared minus 1 plus 6x squared. Okay, so now the minus 6x squared cancels with this plus 6x squared, and the plus 1 and the minus 1 cancel out, leaving me just these two terms. So I get g prime of x equals to the limit as h goes to 0 of 1 over h. And I get to factor out an h from these two. So I'm going to factor out an h, and I'll get a minus 12x minus 6h. Good. So now finally these h's cancel out, and I'm left with just this. So this equals to the limit as h goes to 0 of negative 12x minus 6h. And finally, we get to a point where this is a polynomial. And we know from our work with limits, that the limit of a polynomial is equivalent to just evaluating that polynomial at our limit function, our limit value. So we can conclude that g prime of x is equal to negative 12x minus 6 times blank. That blank is going to be a 0. So the whole thing becomes 0. And so our final answer is just going to be g prime of x equals to negative 12x. Okay, so let's put it together. We have that the second derivative of x is equal to the derivative with respect to x of the first function, which in this little case, just for the purposes of this, I made it equal to g of x. So it's like I'm finding the derivative with respect to x of g of x, like that. And so we figured out that that whole thing equals to negative 12x. So I have that the second derivative of x equals to negative 12x. Okay, so let's put it all together over here. We had that our original function f of x was equal to x minus 2x cubed. And then after we took the derivative of this function, f prime of x is equal to 1 minus 6x squared. And after a bunch of work, we see now that the second derivative of our function, which is equal to the derivative of this derivative function, is equal to negative 12x. Well, if we wanted to continue, then of course we can find the third derivative by taking the derivative of this function, and so on and so forth and so on and so forth. Okay? Okay, so what we can learn from this is that we can build higher derivatives if we just continue to treat our prior derivative as a function, and then apply our limit definition of derivatives to that new function, and then we can find the next derivative. Okay, so I think that should be enough for you to tackle your homework. So please work on your homework and let me know if you have any problems.
Do your homework.